So good morning, everybody. It's 9 o'clock, time to start. There is a little change of plans because our first speaker, Gitta Kutyniok, from the LMU in Munich, cannot come for health reasons, but she has kindly agreed to give her talk online. So good morning to you, Gitta. Great that you are here with us, at least online. And she will be introduced by Klaus Schmidt.
Good morning. I do this with pleasure and with regrets because Gitta Kutyniok was unable to come here, is unable to come here, and I hope you get better soon.
Thank you.
So let me briefly introduce Gitta. She was professor at Osnabrück University from 2008 to 2011, held the Einstein Chair at the Technical University in Berlin from 2011 to 2020. And since then, she has held the Bavarian Chair for Mathematical Foundations of Artificial Intelligence, which you see described up there at the University of Munich. Her research covers a wide range of fields, ranging from, in a sense, classical applied mathematics, like applied harmonic analysis and numerical methods in PDEs, to problems coming under the general heading of artificial intelligence, like deep learning, sparse sampling, and compressed sensing. These terms are as mysterious to me as they probably are to many of you, but I hope that we'll learn a bit more about them. Among other distinctions, she's given a plenary talk at the 8th European Congress on Mathematics in Portorož in Slovenia in 2021, and an invited lecture at the International Congress on Industrial and Applied Mathematics in 2023. In 2022, she was elected member of the European Academy of Sciences. I'm very much looking forward to her lecture, which I hope will shed some light on the challenges and indeed mysteries surrounding many of the concepts in artificial intelligence. Gitta?
Thank you. Thank you so very much. And I very much apologize that I cannot be there in person. So I hope you understand. But I feel very honored to be invited here for a lecture. And I would like to give you a tour through reliable AI, in particular from a, let's say, theoretical mathematical perspective, show you some of the successes, challenges, and also limitations. Now, I think we all know how tremendously successful AI is in various instances, and basically it is already all around us. Think of self-driving cars, think of robotics, think of telecommunications like speech recognition, and then also more sensitive areas, such as the legal system, which, for instance, in the US, already uses AI extensively. Here in Europe, it is more the coming, and then the whole job sector. And then certainly, last but not least, basically every area of sciences is these days using AI, ranging from medicine or biology, astronomy, up to humanities. And everything got a real push lately, also in, let's say, the general public through ChatGPT, as we all know. And I think from my perspective, we are at the start of a radical change of our society, basically in all aspects. Now, coming to mathematics, where I come from, we also witness a change of paradigm. I mean, since 2012, the area of imaging sciences, inverse problems, uses extensively now these new methods for various tasks like denoising, edge detection, in painting, and so on. So basically, I mean, already in 2003, 2004, if you went to a conference, almost 80% of the talks used some sort of artificial intelligence. There's another area which is also extremely impacted, which is numerical analysis of partial differential equations. But you see that embrace these new methods much later. Why? Well, I mean, because the PDE is a rigorous physical model, so why use learning type methods for that? But what turned out is that in the high dimensional regime, these methods are extremely effective and can circumvent often the curse of dimensionality. So therefore, also there, we witness a significant change of paradigm. And I mean, most of the algorithms in the state of the art now use these type of methods. But on the other hand, there are also warning signs. So there was an interesting incident. It's now actually 5 years ago at one of the AI conferences, one researcher, Ali Rahimi, won an award. He gave a plenary speech and said, machine learning, so in particular artificial intelligence, is still at the level of alchemy. And his argument was that researchers, he said, do not know why some algorithms work and others don't. They don't have rigorous criteria for choosing one AI architecture over another. So in that sense, I mean, we are now much further, but still, if you train neural networks, it's a lot of trial and error. So there is still a lot of, let's say, alchemy in there. And we are still working hard to get everything on rigorous theoretical feet. And then there are also these, I mean, let's say, doomsday warning voices, like, for instance, Stephen Hawking said, the development of full artificial intelligence could spell the end of the human race. From my perspective, we are very far from that, and I don't think there's so much danger, but what is the real danger right now is the fact that AI is not at the level of reliability which we aim for. So there are, for instance, problems with safety, and you might have heard in media that there were already various accidents involving robots, and after all, a self-driving car is nothing else than a robot. There are also problems with security. One can hack into these systems, like in self-driving cars, also in hospital systems, modify things slightly so that it cannot be detected, but then, I mean, the self-driving car does radically wrong decision. Also problems with privacy. I mean, all these methods are very data hungry. So in that sense, it is very important to look for privacy violations, and such violations happen basically on a daily basis worldwide, in particular in the health sector. And then last but not least, problems with responsibility. So many of these algorithms are black box algorithms, and often decisions are biased. So in that sense, one can say it's the current major worldwide problem, which is the lack of reliability of AI technology. Now, what is currently done is politics also became aware of this problem, and the international position concerning reliable AI is as follows. So I'm coming from Germany. So for instance, in Germany, we have the AI strategy of the German federal government. Then in the EU, we now have the AI Act of the European Union, and the G7 also included that in their agenda in May in Japan. And there's now the G7 Hiroshima AI process, and also, I mean, an extensive document with, let's say, recommendations on how to set up AI technology in a meaningful and reliable manner. Now, from my perspective, what is essential in all of this is to get a profound mathematical understanding. Without that, I mean, you are always on shaky feet. You will never have true reliability. You need to understand it in its steps. And so in this talk, I would like to take you on a short tour. What is there right now? What are the main challenges? So I would like to focus here on deep neural networks, which are kind of the workhorse for artificial intelligence. I mean, there's also reinforcement learning and so on, but this is basically the main method which is always used. It's not new. It was introduced in 1943 from McCulloch and Pitts, who wanted to introduce artificial intelligence. And what they did was they wanted to mimic the human brain. So they developed models, mathematical models for neurons. So this is an artificial neuron. You have here the input data, and then you have some weights, you have bias term, and you have a function, an activation function, and this then determines the output of this artificial neuron. These artificial neurons are then put together in such an artificial neural network, and if you assemble all the formulas, you get that the neural network is a function of such a type, a highly structured function. It's a composition, as you see, of these affine linear functions and these unimodular activation functions, which are nonlinear and applied component-wise. And so, I mean, during the training process, the three parameters of the system are these weight matrices W and the bias terms B. Now, how do you apply a neural network? Well, I mean, you have some samples available from a highly complex function, which you don't know, and you would like to learn this function, and you would like to use as an ansatz function a neural network. So, for instance, it could be computer scientists like to separate cats from dogs, so it could be the manifold of natural images, where on one hand you have images of cats, cats, which are mapped to the value 1, images of dogs, which are mapped to the value 2, and you have some samples at hand where you also know the labels. Then you split this into a training and a test data set. You set the test data set for now aside. Then you choose the architecture of the neural network, how many layers, how many neurons in each layer, and so on and so on. And that's already what I referred to before. There's still a lot of trial and error, testing and experience which network works best. Then there's a training procedure. It's an optimization procedure, a variant of gradient descent, which is used to learn all these weights and bias terms, which I mentioned before. And once you have the neural network function, then you can take this test data set, which the neural network has not seen before, and check how good it actually encoded the characteristics of, let's say, cats and dogs, to then also deal with images it had not seen before in the correct manner. Now, so that's basically the workflow, general workflow of applying deep neural networks, and that leads us to the key mathematical and theoretical questions. One question is expressivity. So this asks the question, what are the aspects of a neural network architecture which are key? So how many layers should I take? How many neurons in each layer? And so on and so on. So this is usually purely approximation theory applied harmonic analysis. Because you ask questions like, you have the space of functions which you want to approximate. How good can your neural network ansatz function approximate the space? The second is the learning procedure. Stochastic gradient descent works very well to learn these weights and the bias terms, although the problem is highly non-convex. And so that's still a mystery. I mean, there's a lot of theory thrown on that problem, like certainly optimization, optimal control, but also, let's say, a bit more exotic areas like algebraic differential geometry to understand the shape of these local minima. Generalization is, maybe people call it often, the holy grail of neural network theory, because this now asks, once I have trained the neural network, how does it generalize to unseen data? And that's basically also what we want. We want an error bounds in the end for this performance. And so there are usually, statistical tools play a major role. And then maybe last but not least, there's another area which deals with the question that I now have a neural network. I even maybe don't know how it was trained, but I would like to understand its decisions. And that is also for legal reasons crucial, because the EU AI Act requests AI technology to have the right to explain. So the user should be able to ask the neural network or the AI how a decision was reached. So therefore, this area also has a tremendous importance. And so it asks, I have a decision, what are the key features which led the neural network to reach that decision? So let me now give you a short tour through those two areas, generalization, which I deem, maybe one of the most important directions, and also explainability. So generalization typically asks the question, we all know, or maybe not, but large neural networks perform extremely well, and practitioners usually say, take the largest network which fits in your GPU. And so there's a question why this is the case. Why is larger better? And there's this very famous picture, which some of you might have already seen, which shows what today happens. And this picture comes from statistical learning theory. It is very well understood. So what you see here is from the learning perspective, capacity of the hypothesis class. So here the size of the neural network. And this is the error. So the training error, as the network grows, goes down. But the test error, so when you apply it to the test data set, after some point goes up again. And this is this overfitting phenomena, which means the network is too expressive, it has too many free parameters, and now it aims to enclose the data too closely so that if you have new data points, they are likely to be misclassified. So this is very well understood, but now what happens is actually in the modern regime this. You see the left-hand side coincides with this part, but then you have this right-hand side. And what you see here is that the test error again goes down. And so that means the larger the better. So you get here even smaller test errors than you could get here. And people aim to understand this phenomena. There are a lot of tools being used, VC dimension, Rademacher complexity, also neural attention kernels, and so on. I would like to show you now one result, which also, let's say, deals with an area of neural networks, which I find very important, and which is right now, I mean, also extremely hot in a certain sense. And there is one, let's say, part which we can prove completely. So in that sense, I would like to take you to the world of graph neural networks. This is a generalization of normal neural networks because you can always understand Euclidean data as a graph. So graph neural networks deal with graph signals, and the graph signal is a map from nodes to, let's say, RC. So basically, it's a graph where each node has a feature vector. And graph neural networks deal with this kind of data. And they're extremely popular these days because they are used in recommender systems, fake news detection, so social networks, chemistry, molecules, R graphs, and so on. So now, I mean, let's talk about the generalization question here in this more general setting. Certainly what we want is, as said again, I have graphs, signals which are not in my training set. And I would like that the trained neural network then also performs well on those. So let's assume this graph on the right-hand side is here in my training set, but this on the left-hand side is only in my test data set. And then I hope if my neural network is trained on the right-hand side, it also generalizes to the left-hand side. And now you might already guess, I mean, there's a special case now for these graph neural networks, which don't happen in the Euclidean case, because it could be that two graphs model the same phenomena, look alike. Yeah? So this one need to make precise. But then, I mean, we would like to ask the question, now I have two graphs which model the same phenomena. Does a trained neural network have automatically the same repercussion on both graphs? So it's a sub-question of the full generalization question. And so there are various ways to define this model the same phenomena. So for instance, we have a continuous space, and both graphs are sampling from the same continuous space. There's also another approach, which is the so-called graphone approach. So this is basically, graphone is a continuous type of graph, and if two graphs are from the sequence which converge to this continuous graph, then they model the same phenomenon. And so this question we can answer completely. I mean, I don't want to go too much into the details, but let me just say one can set up the graph neural network in a specific way using so-called spectral filters. So we go to the Fourier domain, define things there in a particular manner, and then basically what one can do is one can always, let's say, compare both graphs to the continuous space with overlay them. And as you know, I mean, things are often much easier to deal with in the continuum setting than in the discrete setting. And so basically, the idea is to always go via this continuum setting, compare things, and then one can prove that the error of this transferability, so the generalization error in that case, can be precisely estimated by the transferability of the so-called graph Laplacian and basically the density of the sampling of those two graphs. So we have a very precise error bound in that case and can solve this generalization question there fully. But I mean, the general question is still wide open. I mean, here one can also get similar results if one does not have spectral filters and so on and so on. I mean, it's a lot of research going on, and this is something which I also deem very important, since some areas, like for instance, electron tomography, often do not use neural networks at present because they don't have a ground truth. So they have to completely rely on the algorithm to show them the result. And if there's this uncertainty and we don't have precise error bounds, then this is too, let's say, uncertain for this research discipline. So this is just a short excursion to generalization. So let's also delve a little bit into explainability, because I think this is an area which is very exciting, very interdisciplinary, and also requires a bit more, let's say, deep understanding. So this is what, let's say, very classical methods, explainability methods do. I have an image, a 3, let's say, and I have a neural network which says correctly, this is a 3. And then we are wondering where this neural network based its decision on. And so these explainability methods put out a heat map indicating which pixels were most important to the neural network. And so here the explainability approach says, okay, so the neural network, which made this correct decision, looked at these opening gaps of the 3 and also this area here, which makes sense because that distinguishes a 3 from an 8. But I mean, then you can ask, I mean, so these are, one typically calls them relevance scores. I mean, what is relevance in a mathematical sense? What optimality? We always look for optimality. Can we fairly compare those? Also, not everything is an image. What about other modalities? And what about maybe higher level explanation, since why should only a single pixel be important? Maybe it's actually the combination of pixels which is important and not every single one. So the ultimate vision is to discuss and question the AI as a human about the reason for a decision. We are quite far away from it, but with ChatGPT now, we got suddenly much closer. So for instance, also in my group, use, let's say, ChatGPT to generate queries to the AI. So in that sense, I think there's a hope that maybe we can get there eventually. And also something which I think is often very much forgotten or overlooked. I mean, if you want to use it for legal reasons, for the right to explain, then definitely the explainability approach itself also needs to be reliable. I mean, it doesn't need to only produce nice images, which look kind of fancy, but it needs to be reliable itself, so also in some sense grounded in theory. So let me show you also here one result in this direction. So this is based on information theory, so-called rate distortion theory. If you don't know about that, don't worry. So rate distortion or information theory typically has the general question: I have 2 persons, one has a message she wants to, or some information she wants to transmit it to the second person, who then needs to decode it. And she only wants to transmit as few parts of this message as possible, so that's the rate. And then this person needs to decode it, and he will make an error, and that's the distortion. So the rate should be small, but also the distortion. And we can now phrase this explainability approach in this framework and say the first person has the original image, and both persons have the neural network. Now, the first person transmits parts of the image to Bob, hopefully the relevant part. And then Bob, well, I mean, he first needs to obfuscate it to bring it back to the image size, because otherwise he cannot put it in his neural network. But he can do that also by obfuscating, for instance, with random pixels to not distort the meaning. Then he can put it in here in his neural network and decode in some sense. And hopefully this result is close to this result, so that the message is transmitted. So in that sense, I mean, what one aims for is a small rate, very few pixels transmitted, so a concise explanation in that sense, and also a small distortion, so a small error between phi of x and phi of y. So this leads to this rate distortion function. You want to have transmit very few pixels, but the error should be also kept under control. Now, if you work on optimization, you will say this is not feasible to compute, which is true. So it's very hard. It's NPPP complete, and so on and so on. You can do a full complexity analysis on it. And so if you have something hard, you relax. And so this is then the problem you can solve. We have here, again, the distortion, and we have here, instead of counting the number of relevant pixels, we put now a relevance score between 0 and 1 on each pixel and use the L1 norm, which promotes sparsity. So this is tuned towards giving very precise explanations. And also, I mean, it allows a rigorous mathematical analysis, performance analysis, because it's grounded in theory. And so here, for instance, you see some experiments. You have the image here. You see different explanations. I should say you have a neural network which correctly classifies this as a dog. And then you see the explanations where the neural network looked at, and you see ours is tuned towards sparsity. And so you can also see this, I mean, if you compare this with other approaches, where here you have the number of relevant large pixels versus the error which you make, and you see ours with very few pixels have already very small distortion. You can say, okay, well, I mean, this is a bit unfair because your algorithm is actually tuned towards that. And to a certain extent, I agree. But if you look at the other papers, I mean, this is also the measure they, in the end, take. So then, I mean, you can, from there, extend that even further. So you can ask, why do we take random pixels to obfuscate it? That looks very unnatural. And so there's, for instance, in painting guns, generative adversarial networks, which automatically obfuscate in a much more natural way. And second, you can ask, what about not pixel-based explanations, but clusters of pixels? And so what are natural clusters of pixels in the imaging sense? We have very nice and useful decompositions of images, for instance, in terms of so-called wavelets, which are also the basis for the JPEG 2000 compression standard. And so you can then, I mean, do a wavelet decomposition of your images. So these are some wavelets. Basically, you write your image as a linear combination of wavelets. And then you can put the relevant scores on those instead of just at pixels. And so this leads to this, what we call cartoon X, and it has a very nice comparison to compression. And so let me show you, because in some sense, it's in the spirit of compression, which we found quite interesting. So what is image compression? Just to recall, you have an image, you compute your, for instance, wavelet representation or free representation or whatever representation you like. You take the largest entries, you set everything else to 0. That gives you the compression. And then you hope that from this, if you reconstruct, you get close to your original image. So JPEG 2000 also works that way. Now, in our case, again, we have our original image, we compute a wavelet decomposition, we select the largest entries, and we replace the others now with, for instance, random noise. And then we reconstruct. And certainly these images are not close, but that's also not what we want. We want that they are close if we look through the lens of the neural network. And so in that sense, I mean, you see it's in the spirit of image compression. And so let me show you some things you can do with this. So for instance, this is an application from telecommunication, and it shows you how you can understand seemingly wrong decisions. So what do you see here is you have a city map, these blue areas, these are buildings. The red dots are cell phone users. This white blob is the cell tower. And the neural network computed this black and white background, which is a so-called radio map, which indicates at each point how strong the signal there is. So if it's black, you have a really bad reception. And if you stand here, that makes a lot of sense because there are a lot of buildings between you and the cell tower. But this doesn't make any sense. So you see, if you stand here, you stand actually right in front of the cell tower. Why should you have bad reception there? And then you can ask this explainability approach, what led the neural network to compute, let's say, this black spot here? And so this is the explanation. And in fact, these cell phone users have bad reception. And so what turned out later on was actually there was a building missing in the city map. So the neural network did something correct, but the data was faulty. And so this you can detect that way. You can also understand wrong decisions, why the neural network was misled to a wrong decision. And so here we have a neural network which incorrectly said that this is a diaper, although it's a man with a dog. And it incorrectly said here that this is a screw, although it's obviously a man with a sweater. And so now, I mean, with these, let's say, higher level explanations, I will now overlay it with this higher level explanations. And then we will see what the network has seen to reach this wrong conclusion. So I will overlay it. And what you see here is this looks a bit like a baby. And then the diaper is not that far off. And this looks a bit like a screw. So in that sense, I mean, and then once you detect that, you can correct for that and fine train it to next time, I mean, correctly classify this. Okay, so this was a bit about, let's say, artificial intelligence or mathematics for understanding deep learning and getting true reliability. I would also like to show you a little bit about how you can apply it to mathematical problem settings in a reliable manner, because that's also important, since right now we don't have that level of reliability which we require for certain applications. And so there are two main application areas, which I already mentioned on my second slide. One is inverse problems. Here, typically questions are, how do you optimally combine deep learning with classical model-based approaches, and maybe asking a bit provocatively, is AI capable of replacing highly specialized numerical algorithms in general? And again, I mean, a lot of mathematical areas play a role here. And the second is then partial differential equations. Why do deep learning-based algorithms perform that well in very high-dimensional regimes? So why are they able to circumvent and feel the sense of the curse of dimensional? And here I would like to focus in particular on the first part to show you a bit, I mean, give you a bit the flavor of questions, problems in this area. So entering reliability in problem settings. So let's just very briefly recall what we did before in the classical theory. So an inverse problem is as follows. You have an operator, you have your input image, let's say this image, and then the operator does something with it. Maybe it produces an image where a lot of parts are taken out. And now you have the operator, you have the G, you want to recover F. So you want to invert the operator F. And one classical solution strategy is such a minimization problem, where you see if you minimize this over all F, you aim to solve this problem as accurately as possible. And then you have a second term, because, I mean, you see now in this example, which I have here, you can fill these spots with anything you want. You can leave them black. But you need a second term, which ensures that you get a natural looking image. And so this is a regularization term, where here, for instance, you see this is the philosophy of what's called sparse regularization, that you have a representation system like wavelets. And if you have a natural image, then your representation in wavelets is sparse. And so that's the assumption you put in there. And so, as said here, the regularization term incorporates properties of the image. So which system to take here? Well, I mean, wavelets is one way to go. What we usually did in our cases is to use a more sophisticated system, which is based on the observation that not point structures but directional structures are crucial, which you see in many images. And so these systems, these sugar shearlets, are tuned towards this fact that images are governed by directional structures. They appear in any position on the image, in any scale, and also any angle. And so you can show nice results that for certain model classes of functions, these also fulfill the optimal compression rate. And if you like to play around, I mean, we also have what I show you in a few minutes. If they're using deep learning, we have on this webpage shaded.org. Okay, so this is the classical approach, or one classical approach, sparse regularization with shearlets, for instance. And let me show you one use case that this often reaches boundaries. So this is computed tomography. Maybe hopefully you have not experienced it yourself. But yeah, so how is, let's say, the human body measured? So this is done through the Radon transform. Line integrals are computed. This provides a 1D function, and this is one slice of the sinogram, and then everything is rotated. Yeah, so you compute it from every of these 180-degree angles. Now, and from the sinogram, the task is now to recover the interior back. Now, so these are the measurements. But what is often the case, and what could be the case, is that you don't have the full sinogram. Maybe you also want to expose your patient not to too much radiation. You only want to compute every second angle, and that leads to low dose CT. But maybe it's even more serious in electron tomography. You have a whole missing angle. Because, for instance, you have your probe sitting here, and now if you turn your device, at some points the rays cannot get through it anymore. And so you cannot turn 180 degrees, but maybe only 130. And so the effect of this you see here, if you have a 60-degree missing angle, this is the original image. If you have a crude reconstruction, it looks awful. If you do what I discussed with you before, sparse regularization with shields, it looks better, but it's still very blurry. And the reason is such data is just too complex to precisely model it and get a good regularization. And so here, deep learning can have an edge, because here this method reaches its boundaries. And so there are a lot of different methods which basically combine classical methods with new methods. I mean, certainly if you want to get rid of, let's say, the classical methods completely, you train a neural network end to end. But then, I mean, I'm wondering, you know a lot about the physics of your problem. I mean, why throw it away? And also this is, I mean, often causes, let's say, instability problems. You could incorporate your operator K into the neural network. You could also use this algorithm, this optimization algorithms, which I showed you. You can break it open and replace parts with neural networks. It's called plug and play. These are, I might call, supervised approaches, because you train the neural network on the full data. Here you could, I mean, I might call them semi-supervised approaches. You could encode the regularization term by a neural network, so that's called adversarial regularization. So then the learning algorithms requires not, let's say, the full data, but only a set of labels in that case. And then there are also unsupervised approaches. Basically, I mean, so this very interesting work, deep image prior, where basically you don't train the neural network, you use it to parameterize your solution as the output. So let me show you one result, one strategy, which I think is, I mean, which we usually advocate concerning reliability, because then you use the neural network only where you cannot get further with classical methods. So basically use it when all hope is lost, in a sense. So here, the first step, high-level step, you use model-based methods as far as possible, as far as they are reliable, complement with AI-based methods when they're necessary, combine both worlds. So therefore, you get your theoretical guarantees from the model-based methods, because AI is not at that level yet. You know exactly what is computed. You get a better performance because for instance, deep neural network has a limited, let's say, range of data it needs to deal with, and doesn't need to process the entire data. It's less than a black box. So now, if you go to this limited angle computed tomography example again, the model-based methods, we use sparse regularization with shearlets as a first step, and then we process the output again to detect what has not been reliably recovered, and only use the nested deep neural network for that, and combine both. And so you see here, for instance, I mean, how it looks. We already saw those two. This is something where you train a neural network end to end. And here you see if you combine those both worlds. And so you see it's far better than anything which you could do before. Okay, so let me come to conclusion. So what we saw were, I mean, how you can make AI reliable, and also how you can apply it reliably to certain problem sets. One aspect which I think is very much overlooked right now, and which I would like to mention in the last few minutes, are limitations. Because, I mean, this is not a Swiss Army knife. There are limitations, and I think it's very important to also talk about those. And so these are my last slides, which I would like to show you. So as said, AI is not a Swiss Army knife. And one can ask, because we train everything now on digital hardware, CPUs, usually GPUs, so we break basically everything down to zeros and ones. Although the problems we solve are typically of a continuum nature. And so certainly this needs to cause some problems. And so you can ask, I mean, you can aim to understand that from a computability viewpoint. And so there's this whole area in computer science, computability. So basically, in rough terms, a computable problem is one for which the input-output can be computed on a digital machine for any given accuracy. If it is not computable, certainly you can run your computer on it, you will get something out. But then, I mean, the precision might be limited, and also you don't have a guarantee for correctness because you cannot compute it. Yeah, I mean, you will get something, but it's, again, you don't have reliability, definitely. And so there's a model for digital machines, which is the Turing machine, and not going into the details, it's accepted that this is the correct mathematical model for any digital machine. So what you can compute on a Turing machine, you can also compute on a digital machine, so on a computer, and vice versa. As said, I mean, typically the problems in science are more of a continuum nature, in particular also concerning inverse problems. So what we could show is that, in fact, the solution of finite dimensional inverse problems is not Turing computable by a deep neural network. Yeah, so this is, I mean, a limitation which, I mean, one cannot overcome. And also, it is not a problem of the inverse problem, it is a problem of the hardware we compute on. Which typically, I mean, as we all know, computations are performed almost exclusively on digital hardware these days. So we cannot find an algorithm, a general algorithm, which computes the solution for any given accuracy. The output is not reliable, and it might also be one reason why we see these instabilities in AI and in the output of neural networks. So this is quite disappointing, but there's also a way out, because what one can show is that if one go to analog machines, which are able to handle, let's say, for instance, real numbers, and there's also a model, the so-called Bloom-Smale machine, the analog, basically, of the analog of the Turing machine, and so things become then computable. So this points towards that if you really want to have computability, reliability, you might need to require novel hardware, and there are exciting developments like neuromorphic computing, biocomputing, quantum computing. And so let me also mention, I mean, one other problem with current hardware, as we all know, is the huge energy consumption. Yeah, I mean, these GPU centers are extremely energy hungry, and within 10, 15 years, we will not be able to support them with the word energy production. Whereas, for instance, neuromorphic computing is much less energy hungry. So in that sense, I mean, not only from a computability viewpoint, but also from an energy and sustainability viewpoint, this is a key direction which I think this whole field of AI will and needs to go. And so if you drive this further, you can show that many problems, also classification problems, computing the pseudo-inverse, some instances in partial differential equations, I mean, all have this problem to a certain extent with computability. And so in that sense, I mean, if you really want to get to truly reliable AI, you need to consider next generation computing. Okay, so let me conclude. I mean, from my perspective, we actually live in an exciting time. I mean, AI shows impressive performance in real-world application, but we have this reliability problem. I showed you a bit, I mean, the mathematical perspective of it, what are the key theoretical directions. We delved a little bit more into generalization, explainability, and also inverse problems. And finally, we discussed also general limitations, which, as I said, is an area completely or often overlooked. And so in that sense, I think from my perspective, a vision, important vision for the future is to consider also the hardware component and go to next generation computing. So let me, since we talked about reliable AI now for a long time, let me also mention just the previous, I mean, the almost last slide, that we just started basically in Munich, a school, a Konrad Zuse School of Excellence in exactly this area, reliable AI. You see, mathematical algorithmic foundations are one key area which we work on. And so the idea is to train generations of AI experts who are not only technically brilliant, but also aware of the importance of AI's reliability. And I think something like this needs to be done much more because we really require experts who are aware of what it takes to be reliable. And so this is set up here, I mean, our case between both universities in Munich. And so let me stop here and thank you very much for your attention.
Thank you very much for a most interesting talk, which answers some questions and opens up many, many more. But let me invite questions and suggestions.
So I have a question regarding this intriguing behavior in the generalization problem, where there is this turnover in the cost function. So is this a universal phenomenon? Do you expect this always to happen when your model, your network is large enough?
So I mean, there was a problem with the connection. So if I understood you correctly, you were asking about this double descent curve, whether this is a phenomena which always happen. Is this correct? Or?
Exactly.
Yeah. So I mean, I think it depends also a bit on the architecture of the neural network. As said, it's not really fully understood. But still, I mean, if you see, for instance, also concerning foundation models and so on, I mean, large networks have a huge edge because they have more capacity. And also there's, I mean, there's another area of research which aims to understand this implicit bias, which is in the training of the neural network, so that basically you don't overfit, which prevents this overfitting phenomena. But in general, I mean, so from what I know, I mean, this is actually true for most neural networks. I mean, the larger, the better. I mean, if you enlarge it in an unfortunate manner, let's say you just have one layer and then you put, I don't know, a billion neurons in this one layer, it will not work. But I mean, you also need to increase the number of layers. But in that case, I mean, you will typically encounter this phenomenon. Yeah.
So is there some kind of phase transition going on in the model when this happens, or what happens?
Yeah, I mean, yeah, so you can view it as a phase transition. So if I go back, I mean, you see, so if you look at this image again, yeah, so basically, I mean, the phase transition would be here in a certain sense. Yeah, so when there's this what's here called interpolation threshold. Now, so after some point, I mean, it basically overcomes this overfitting phenomena, and then, I mean, this implicit bias kicks in. So yes, I mean, there's a phase transition in that respect, exactly.
Just a related question. Are there some methods to predict for a given problem and a given neural network architecture where this phase transition will take place?
Yeah, so that I'm not aware of. I mean, certainly there are some, let's say, some approaches which for some certain cases aim to understand this curve, and then in that case, you know, but I mean, there's no general, I mean, as far as I know, no general method for any neural network to say before when this transition happens. I would say, I mean, so you see, I mean, what you need to do here is, I mean, if you want to look at this graph, I mean, you need to increase the network. Let's say you have a neural network of a certain width, and then you increase the number of layers. But as far as I know, I mean, there's no result which says after this number of layers, I mean, this a general result which after this number of layers you encounter this phase transition and go further. But I mean, partial results are there, but not, I think, the general.
Thank you. Another question, yes, please.
To get away from the double descent, I have a question about your result. Can you hear me? About your result where you showed that problems from scientific computing can be non-computable on a digital machine, which seems like a very scary result. Is this some sort of, is the proof such that there is some contrived setting in which it's not computable? Or is it generically most scientific problems? I'm asking about the measure of these uncomputable problems. Is this a problem that is just produced in order to make a proof work? Or Or am I supposed to think that most problems in scientific computing will run into this barrier threshold?
I mean, there are some, I mean, it's not, I mean, I wouldn't say that there's most problems. I mean, you can also always, if you aim for a certain particular accuracy, then you can design an algorithm for that particular accuracy. If you get away, let's say, with 1/2 accuracy, I mean, then you can design a specific. So here, this says there's no universal algorithm which gives your output for let's say, any given accuracy. Also for special cases, let's say you have more information on your inverse problem, then, I mean, things also can become computable. This is, let's say, if you look at general finite dimensional inverse problems, then you can show this non-computability issue. And in fact, I mean, you can then also show that, I mean, for certain instances, you might be always, let's say, you have a loose, let's say, error, which I mean, a consistent error, which you will make. And this error is actually not that small. It's sometimes one fourth or something of that type, which is not, in a sense, not acceptable for a lot of settings.
Thank you. I think we have to move on. Thank you very much for a very nice lecture. It's a pity we can't ask you questions over coffee a little later, but maybe another time.